Okay, so we just finished up looking at problem one. Let's look at problem two now. Bin analysis problem used for many applications. We've been building your spreadsheet skills to handle this problem. I know you can do this. Okay, I'm pumped. I'm pumped. Oh, I remember this bad boy. It's a good one. Okay. Wind farm is contemplating an installation of a combined compressed air energy system to store energy is compressed during off-peak hours. Then use the compressed air in a combustion turbine. Sweet. Natural gas and sell energy during on-peak hours. You've been asked to build a model for 1 day. Cool. And determine the daily energy costs and energy revenues using the following assumptions. As compressed air is withdrawn from the cabin, assume this compressed air decreases equally over time. I love this problem. As the cavern air pressure decreases, the CT's heat rate increases, which is a bad thing, right? Or not?
Yeah, less pressure and more opposite efficiency. Heat rate.
Well, let's go back to heat rate. Hang on. Let's think about this. Okay, so well, it kind of gives it to us. All right. Create a table in the spreadsheet. The whole energy and one bar pressure between water table. So starts turbine output of 50 must increase. Okay. Okay, this is not that bad. Okay. So let's start a new one. Problem 2. Okay, so what we're looking at, 1 bar from 75 to 50, no problem. So 75 equals, and I'm just going to say here, if you want to watch. So the easiest way to work this Excel to make this guy is just say equals dink minus 1. I'll make that a little bit bigger. So all I did was typed in 75, and down here I just typed, well, I clicked on D5 and I said minus 1. So if I take that now and drag it, I got her down to 63, and I'm just going to keep going. There, I luckily hit 50. Okay. I know I'm going to start at 45 and end up at 8,000. 4,500. So this is going to be PSI here. And then my heat rate, let's call that HR. It's going to be, I'm going to start at 4,500. I'm going to end at 8,000. So we'll first write it in, and then $4,500. Okay. Now, but let's go to the trouble of making the function. So we have to figure out So heat rate equals M times pressure plus heat rate naught. There's your Y equals mx plus b. So what we know is that we got pressure over here, we got heat rate over here. And so we know that at a pressure of 50, our heat rate is 8,000. Right there. And we know at a pressure of 75, our heat rate is 4,500. Right here. Okay, so what does M equal? Well, this point right here equals 50, comma, 8,000. And this point right here equals 75, comma, 4,500. So M equals, we're going to start, you always start from the right, 4,500 minus 8,000 over 75 minus 50. Now, the numerator is going to be positive, the denominator is going to be negative, so the slope is going to be negative. So go back to our calculator. Not sure why I'm using a calculator when I've got Excel, but it's okay. 4,500 minus 8,000 equals, divided by 75 minus 50 is 25, equals negative 140. Equals negative 140. So negative 140 is the slope of that line. So we'll come back and say HR equals negative 140 pressure plus HR naught. Well, how do we get HR naught? All we have to do now is substitute in a couple values for HR and P, and we'll get it. So we can just pick whatever we want. We can say 8,000 equals negative 140 times 50 plus HR naught. So in this case, HR naught equals, and all that's going to be is whatever the heat rate is when the pressure is zero. You're never going to hit zero, so it doesn't really matter, but we still need to figure it out for this particular thing. So we're looking at 8,000 plus 140 times 50 equals, so plus 7,000. 7,000. So we end up with HR equals negative 140P plus 15,000. So that's our equation that we're looking for. Okay, so HR, let's just sneak, so M is right here. We got our M as negative 140. Negative 140. And we've got our HR naught as 15,000. Hello, 15,000. So equals M times PSI plus HR naught. We get fancy and put a subscript on that guy. Control 1, subscript, okay, enter, fine, home. All right, so I figured it out once. Let's see if we hit our target. We'll slide her all the way down. Oh! Oh, I know I did it wrong. I just didn't pin it. I didn't do a reference on that. So $sign. $sign. Try again. Boom. Okay. So just to review, we know we're starting at 75 psi. The heat rate is 4,500. We're going to drop down to 50, and our heat rate is going to go to 8,000. BTUs per kilowatt. So, yeah, so as we get less pressure, we're going to have a higher heat rate, which is actually inefficient because we're putting more BTUs in to get fewer kilowatt hours. Because remember, let's just go back to the physics of this problem. What's going on is we've got here's our turbine. We got air coming in, and we got natural gas coming in. And what's coming out is electricity, kilowatts. Well, the way we want to think about it is kilowatt hours. So what's really going in here in the form of the natural gas are BTUs. And we can go out online and see, okay, how many BTUs are there per volume of natural gas? So you can think of energy going in, energy coming out. You can think of it as power going in, power coming out. But when we have, let's think of it this way, back to this guy at 75 psi. So let's just look at it up here. So 75 psi is going to give us a heat rate of 4,500. 4,500, and again that's BTUs per kilowatt hour. Now let's flip that over because I want to think of it in the opposite sense. The numbers are going to be small, but that's okay. So let's just do 4,500, and let's throw a 1 over x at that. Equals 0.000222 kilowatt hours per BTU. Now, if we throw 50 psi at it, so less pressure, that's going to give us a heat rate of 8,000 BTUs per kilowatt hour. Equals, or I should just say it doesn't equal, it's the reciprocal. So if we do 8,000, 1 over x, 0.00125, 0.0000125 kilowatt hours per BTU. So think of it, again, just like efficiency. The BTUs are going in, and the kilowatt hours are coming out. And so, so we can think about an efficiency. So the higher pressure is more efficient. That's kind of the whole point. You want a whole bunch of air in there so you can make a whole bunch of energy coming out. Okay, so we built this function. What's next? 1 bar. Oh. So it's not PSI, it's bar. Doesn't matter. It makes more sense though, much higher pressure. And so this is actually 50 atmospheres and 75 atmospheres. Okay, not a big deal. Hold turbine at 55 megawatts. About 50 megawatts, okay. So now we're looking at power equals 50 megawatts. Equals well, here's how we'll do it. 50 megawatt hours per hour. Right? Equals 50,000 kilowatt hours per hour. Equals, so let's just get from so we're looking at 50,000 kilowatt hours per hour. And it's got to get from BTUs to kilowatt hours. Let's do kilowatt hours to BTUs. $34.12. 3412 BTU per 1 kilowatt hour equals, so 50,000 kilowatt hours per hour times 3412 equals 170 million BTUs per hour. 176, 170 6 BTUs per hour. Kilowatt hours cancel, kilowatt hours cancel. So that's how many BTUs per hour.
It's pretty pricey.
That's a big one.
$4 per mega BTU. Oh, so that's not that bad. So that's only 170 mega BTUs. That's what I say.
Yeah, the BTUs are weird. Let's look at there's let's see, it's MBTU. There's MBTUs and MMBTUs. Here we go.
Yeah, I was wondering about that.
Yeah, it's a little weird. Yeah, MBTUs is 1 million BTUs. What's this thing? It says MBTU is occasionally expressed as MMBTUs, which is intended to mean 1,000,000. So, yeah, I have no idea why that got so messed up, but a BTU is still a BTU. Let's not get too crazy with it.
Gotta make things harder for laymen to understand energy.
Well, it's job security for those in the field, right? Cheat somebody out of 1,000 times more
Yeah.
money.
No, that's MMBTU.
One day. Heat rate.
Calculate the time duration. How long it takes to go from one pressure to another.
Reach pressure bin, calculate the heat rate. Why am I not getting that? Oh, wait, we already got the heat rate.
Yeah, got that.
I think maybe I have it, I just don't know it.
Time duration.
So we know the BTUs per hour. I know it's right in front of me. I'm just getting a little tired here. Hang on. let's just look at it just very simply. So power equals energy over time. Time equals energy over power.
BTUs.
I'll take a quick break and figure this out.